All right, good day, everyone. Today, I want to share with you how you can use serverless functions to do big data applications and how to think about things that are not necessarily, I've got a web server, or I've got like a set of step functions, but instead, how can we actually put serverless to work in larger data analytics applications? So today, we're going to talk about four things. First of all, we're going to talk about how serverless can be helpful to kind of these big data workflows. Secondly, because I come from a reliability engineering background, we're going to talk about all the things that go wrong when you do that naively without consulting anyone or bumping into all the obstacles head first. Thirdly, we'll talk about how to do this in a safe way that makes it possible for you to safely experiment. And then fourth, we'll talk about some of the experiments I and my company have done over the past couple of years to improve price performance by applying some ARM64 processors to our serverless workload. So let's talk first about what is serverless for, like both traditionally and kind of what's our new application of it. And maybe just to quickly define serverless, because I know the definition of serverless can be contentious. What I'm going to say serverless is, I am not an expert in this. I don't necessarily go around telling people, you should totally do serverless. But my definition of serverless is that it is a runtime environment where I can set my application running. I don't have to think necessarily about what hardware is it running on. I don't have to think about manually provisioning it because the cloud provider takes care of that for me. And in Honeycomb's case, in the kind of case study that I'm demonstrating today, we use AWS Lambda. I understand some of you may use Azure Functions, and that's OK too, right? Like, basically, the core idea is whichever cloud provider you're using, you are offloading that kind of work of maintaining and scaling the runtime to your cloud provider. So specifically in our case, we started wondering, could we use AWS Lambda for optimizing our custom data store? But, again, like, who is this serving? What's the purpose of it? So why are we running a custom data store? So what is Retriever? Why does that matter? So Retriever is a columnar data store that we wrote that is very similar to ClickHouse. If ClickHouse had been around 5 years earlier, we might have chosen to use it instead. But the core idea is that Retriever is a distributed column store that enables us to do real-time event aggregation and analysis. So think, something like Google Analytics, think something like Splunk, think something where you are trying to process data. And also, because all of our services at Honeycomb are named after dogs, here's a picture of my golden retriever mix. So that is Flurry. Aw. So what are we using this real-time event aggregation for? Because, right, like you could be analyzing clicks on your website. You could be analyzing the performance of your store sales. But in our case, we are doing this for the observability purpose. We are trying to interactively query trace spans and logs. So this probably is an opportune moment for me to introduce myself. I'm Liz. I'm the field CTO at Honeycomb, and I'm also an AWS community hero. And I hail from Sydney, New South Wales in Australia and Vancouver, British Columbia in Canada. So you've actually caught me kind of in the middle between those two places right now. So at Honeycomb, we help people understand how their systems are behaving and what's going on inside of their systems. And historically, we've thought about kind of monitoring as you look at your application and your system keeps track of what's going on. Is everything normal, or are there situations that are abnormal that we need to send alerts on? Which is well and good, except for today we live in a much more complex world, and maybe you might want to see things that you didn't anticipate in advance. Maybe you might not want to have everything pre-aggregated, but you might want to post-aggregate to figure out what happened after the fact, rather than having a predefined rule saying, I only want to count up my HD 500s, or I only want to group things by build ID. And instead, to have the flexibility to choose to group anything up. So what do I mean by this? Well, again, this is just to give you an idea of the use case that we are using serverless functions for. So I have an application here. Let's see, roster. So this is my EVE Online Alliance, and because we are an EVE Online Alliance and we like to have fun by writing software, we have written our own HR software. And our own HR software is measured and instrumented with this technology. So I can go in and I can ask, hey, what's going on? What's going on with this page load? Why is it so? So I can go ahead and run those queries. And because I want to get super meta here, so this is a set of queries that this is a set of requests that just happened because I went and accessed this demo application, as it were. But let's go one level deeper, and let's introspect into what happened when I clicked that Run Query button, or what happened when I went and viewed this trace. So I can go here, and I can look, and I can see, specifically for queries that I issued, what's going on with those. So I might be able to ask, what's going on with the performance of that specific time that I clicked Run Query. And sure enough, we can see that there's a lot of stuff that happens when you run a query. So that's kind of the core idea that we're getting at here, is that if you have stored all this raw data, you can go ahead and look at it after the fact. And it doesn't matter whether it's observability data. It could also be your shop sales. It could also be information on who's accessing government benefits. But the core idea here is that the faster you make this feedback loop, the easier it is to do kind of hypothesis-driven development. Because there was this talk this morning, right, in which there was a discussion of understanding your software systems using the scientific method, and that you do 80% of your job is writing software, writing features, and then the other 80% of he's on the audience, great. And then the other 80% of your job is debugging those features when they go wrong, right? So this is the kind of thing where if that other 80% of your job that you're doing in your 160% time winds up taking forever and being a giant pain, then you're going to have a much less happy time at work. So it's important to have observability if you have complex systems, because you have to be able to understand what's going on with those complex systems and be able to very quickly iterate and hone in on, no, my hypothesis about it being in this part of the system is wrong. It's actually in that part of the system. So at the end of the day, the fundamental data type that we're ingesting to generate all of this data that we're using serverless on is we're ingesting a bunch of OpenTelemetry data, and we're storing it into our columnar data store. And hopefully people are asking questions and getting valuable insights. And of course, because this is the year 2024, of course, there is AI sprinkled on this too, because our investors have told us that we have to do that. So why did I say speed, right? Why did I say that it has to be fast? Well, how many of you have ever sat there and run a Prometheus query or run a Splunk query? OK, yes, but how many? OK, of the set of people who have run like a Prometheus query or a Splunk query or a Datadog query, did it take 30 seconds, 60 seconds, or did it come? Yeah, that hand's up, right? Like it took 30 seconds, 60 seconds. What if you could click the Run Query button, take a sip of water? By the time you take the sip of water, you have the answers to your question that you just asked, right? If you get jerked out of that state of developer experience and flow every single time that you have to wait for the system to tell you what's going on, that's going to really make you feel not very happy as a developer, right? So there's a lot of magic that we wound up trying to do under the hood to make this feel as seamless as possible. We're a Go shop primarily. We don't really use that much .NET. That's kind of a function of being a business in North America that started in 2017. But kind of the core thing that our users expect us to do is they expect to kind of ask this kind of arbitrary question. For instance, like, hey, show me all of the requests that, let's group this by URL. Right, so show me all of the requests that are to this particular dashboard page, which says queue summary. Right, show me that specific thing. Right, so I'm kind of formulating these queries on the fly and expecting the query engine to act on it really fast. So this originally was inspired by a system that the developers at Facebook, which is now called Meta, came up with, and that system is called Scuba. So Scuba was a system that was tremendously complex, and also, though so expensive, only Facebook could run it. Specifically, what it was doing was it was storing all this data in memory so that it could give people lightning-fast results. The other thing that the developers at Scuba did was they didn't really prioritize developer experience. They just said, we're just going to put a command line UI on it. You can write a SQL query on the command line, and that's good enough, right? Like, no one needs developer experience. So we decided that we wanted to try to expand the system and to make it something that would be affordable to mere mortals. So initially, the way that we decided we were going to do this was we said, OK, we're going to buy a bunch of EC2 nodes. And we were specifically going to buy a bunch of EC2 nodes that have local NVMe solid-state drives on them. And surely that's going to be several orders of magnitude of cost lower than storing all the data in memory, right? Like that's going to be cheap enough for users, right? So there is still some sharding. There is still some capability for horizontal scaling, right? Because you can't fit everything on one single machine, right? Like machines only scale vertically so big. So the way that we decided we were going to approach this was that we were going to use Kafka to farm out the data horizontally and just splash it out across as many nodes as we needed, whether it be 12 or 30 or 50. I think that fleet grew to something like 70 different nodes. And the idea was, you would send along the specification of what is the user trying to read, what's the data that they're trying to access. And you would have each node go and query its local NVMe storage and return a result, and then all of this would get merged back together. Glorious, right? And the other trick that we thought was going to be really helpful, which we borrowed from Scuba, was the idea of the columnar data store, right? The idea that instead of being row-based, where you store each log line of data kind of one at a time serially, so that you can only access each individual row and each value within the row by looking up that row first, we said we're going to split up all the data. So if there is a given key value pair that's in each log line, we're going to store all of the values for each key together. Because chances are there's some duplication there. Maybe there's the opportunity to do some compression because maybe the same HTTP URL is accessed multiple times by different users who are, and therefore you can say, OK, this URL is repeated many times. We're just going to condense it into a single identifier. But the other thing besides the compression benefit of this is that it allows you to say, let's go ahead and make it so that I can separately access all of the HTTP URLs, and I can separately access all of the build IDs, but that I don't necessarily need to keep the data on user agent right next to all of the data on the HTTP URLs or the build IDs. So if someone comes along and says, I am specifically interested in build IDs, you don't have to sift through all of that extraneous data. And that really, really helps improve the speed because then you're not scanning data that's extraneous. The other crucial insight is that you want to be able to reduce the amount of data that you're querying based off of the time range, right? It doesn't make sense to read data that is between 59 and 60 days old if I've just asked a question that's only about the most recent hour of data, right? I only need to find any particular files on disk that might overlap with that 1 hour time range that I'm looking at. So those are kind of some of the tricks that we initially did to try to make this a commercially viable product. And this really kind of enabled people to ask questions that they couldn't before. And today, there's actually this really wide plethora of solutions out there that are based off of ClickHouse because the folks at Yandex open sourced it, and people found it very attractive and useful for being able to do this kind of workload. But we actually encountered an interesting problem in 2019, which is that more and more data was coming in, and that data stopped fitting on the individual NVMe solid-state drives of each box. And the data that was, we were aging out the data that would no longer fit on disk. And it turns out that it's not quite as useful if your tool says for data that's 2 hours old, oh, I don't have that anymore, like it expired. It's like, great, like what use is it if I can't even query back 24 hours? So the first thing that we did here was we said, OK, maybe we don't need to keep all this on local NVMe solid-state disk. Why don't we go ahead and implement data tiering? Let's just go ahead and tier all of that older data to S3 because, chances are someone's not going to look at the data that's 60 days old very often, but people are more likely to look at the data that's 2 hours old or 3 hours old, and we can kind of prioritize keeping the fresher data on local disk, and if we need to scrape data back from S3, that's OK. So yay, people can now keep 60 days of data rather than us saying, sorry, we ate your data, you have too much data. Yay, people can run queries over 60 days, except for the site reliability engineer in me is cringing because, oh no, people can run queries over 60 days. And suddenly we've gone from, I can finish running a query in less than the time it takes to take a drink of water, to it's sitting there and spinning and spinning and spinning and spinning. So fundamentally, the problem here is a mismatch between the amount of compute and network bandwidth that was available on each of our local nodes versus the amount of storage in all of S3 that we could potentially pile up from our customers. And fundamentally, this is a problem that I encounter in my household as well, which is that my dog really wants to play with all of her toys at once simultaneously when she's like romping around and being like, I'm going to go and chase the thing. Oops, I forgot to bring it back to you, right? And you just throw more and more and more toys out of the basket into your house. And then the dog is tired, and she goes to sleep, and she's like, actually, I don't want to play anymore, right? And now you're stuck with all of these toys scattered all over your floor. So fundamentally, we knew that we couldn't just keep on scaling out our compute fleet because people are querying that data a lot less often than they're writing the data. So the answer to this turned out to be serverless for us. That serverless was something where the cloud provider has compute lying around, and they're willing to lease it to you for a fee and only charge you for the time that you actually use. So we were able to say, OK, if the data has aged out and it's stored on S3 rather than stored on local disk, then why don't we go ahead and farm out that work that's querying across all of these files that are stored on S3. There's no reason that it has to be queried by the node that originally wrote those files to S3. But instead, you can just have an arbitrary compute task that's running somewhere, I don't care where. Go ahead and pick up the list of files to read, and to pick up the kind of query expression that you want to run against it, and go ahead and ask and then merge those answers together. So the only data that really matters for locality is the most recent data that hasn't been tiered to solid state yet, or tiered to S3 yet. So this has a really beautiful property of suddenly, instead of a linear or superlinear pattern of query latency, now suddenly it's sublinear, that you can query an order of magnitude more stuff and have it take less than an order of magnitude more time. And amazingly enough, I don't understand exactly why they decided to let us get away with this, but they are willing to rent compute to you in 1 millisecond units, which means that if you don't actually use that compute for any given time range, you don't pay for it, even though they're keeping your workers nice and warmed up for you. So that's kind of the, in a nutshell, story of how we used serverless computing to try to make our query engine run faster. So there are some caveats and asterisks here. Now we're getting into part 2 of the talk, which is let's talk about some of the asterisks in this beautiful slide that says, oh, it's only 3 to 4 times as expensive, and it typically returns within 2.5 seconds. Well, what happens when that goes a little bit awry? So we experienced very, very large growth from 2019 to carrying over to the current year in 2024. So we've grown by more than an order of magnitude in that time, both in terms of how much data we're ingesting, which impacts the scale of the system, and also how much people are querying that data. So I actually ran the numbers, and yes, we are actually petabyte scale. We passed 1 petabyte of data under management about a month ago, which is pretty exciting. And here's kind of where things break down when you are starting to use serverless functions to look at a petabyte of data. So first, let's talk about the scaling. So yes, it turns out we would love it if AWS Lambda kept our workers warmed up 100% of the time across their entire fleet. But guess what? They have other clients besides us too, right? So in general, your serverless provider wants to keep an appropriate number of workers that are pre-scaled and available to you. And they might let you cold start more workers and kind of boot up more workers if your load increases. But their kind of operating theory is based off of web services or things where you're using an API gateway to invoke a Lambda, where the load is a little bit more predictable. So their idea is essentially, they will raise your concurrency limit if they see that you're repeatedly hitting your limits, but that if you burst over your limit, they reserve the right to send you an error message that says, slow down, try again later, like, we're not ready for you quite yet. But when you have a situation where someone comes along like me, right, like someone comes along like me and runs a query, and it tries to invoke 10,000 different tasks, right, that might breach our burst limit, but only for maybe 5 seconds, and then that load goes away. And originally, it was 1 minute of sustained load that was required for the concurrency limit to be bumped. But the good news is, at least on the Amazon side, I cannot speak to the Azure side, they changed this recently to be like 10 seconds, that if you are exceeding your limit for 10 seconds, they'll give you 1,000 more concurrent workers. And if you're still exceeding your limit 10 seconds later after that, they'll give you another 1,000 concurrent workers. So it actually turns out to be less of a problem for this kind of workload today than it was when we originally started doing this 5 years ago. And one of the fun things is because we dog food, we can actually verify how much real-world concurrency are we actually seeing from the cloud provider, and does it match the negotiations and expectations that we have with our cloud provider about what they've said they've capacity planned for us? And that, by the way, is a little bit of an asterisk, right? The whole theory of serverless is you walk up to your cloud provider and you say, 1 compute, please, and it just gives it to you, right? But here we are having to manually capacity plan with our cloud provider because we are this odd shape that is very bursty, so they want to understand when are we scaling, how are we scaling. So there are limits, but the key thing that you can do if your workload is something that is, that is a retriable workload, which a read-only workload is fundamentally retriable, you can just keep on retrying until the request eventually succeeds because your rate limit has been raised high enough. And yes, talk to the people at your lovely cloud provider if you're going to be using serverless functions to do big data analytics. OK, let's talk about the next thing, cold starts. So as I mentioned, most of the time, if you are running a fairly predictable workload, your cloud provider will keep a pre-warmed copy of your code that's running and ready to receive a request at any given time. But that's not always guaranteed, so sometimes you have to do a cold start. And when you do a cold start, you are paying some amount of time to do static initialization. So people invest a lot of effort into trying to reduce the impact of a cold start, because you cannot guarantee that you're not going to have a cold start. So the best thing that you can do is kind of front load as much initialization as possible. Maybe that means serializing a bunch of state and just loading it into memory right away, as opposed to fetching it from a remote host. Maybe it can mean deferring some of that execution until you actually need it, right? Like, there are a number of techniques that can be really helpful. But at the end of the day, it is still, even in this kind of worst-case scenario of 13 milliseconds, 50 milliseconds for a cold start, that is blazing fast compared to the cost of spinning up a new EC2 instance or spinning up a new Azure Compute instance, right? That if you have to wait for Linux to boot, that's going to take on the order of seconds at least, right? Whereas we can get this compute fresh delivered to us and ready to execute a request most of the time within 50 milliseconds. And the compute on the back end, right, like, because again, like, serverless functions abstract this away from us, they'll go ahead and allow some of these workers to fall back asleep rather than killing them after each request is done, which means in an optimal situation, you wind up with a worker being hot and available to run a request whenever. And I actually went and pulled this morning. So you can actually see that roughly, it looks like we have, at any given time, there are 50,000 workers that are kind of pre-warmed for us. And they'll be kind of pressed into service when there's a query workload. And then if there's not a sustained query workload for a while, then they'll suddenly shut them down, right? They'll say, OK, like, we're no longer allowing you to keep these 50,000 workers suspended, because it still is consuming memory, right? Like, even if it's not actively consuming CPU, it's still sitting there consuming resources. So they manage this whole process of capacity planning to shut down workers that we're not using. And sure enough, you can see, right, like, after it's been like 5 minutes without someone running a query, they'll cut the number of workers down to 10,000 and then 2,000 until someone starts querying again. OK, the second kind of pedantic systems operator thing. 90% of our queries return within 90% of our queries against AWS Lambda return within 2.5 seconds. Turns out P90 is not really a great metric to use because it means 10% of your users can be having a worse experience than your P90. So, it's one thing for me to say, our P90 is great. Everything is, as fast as taking a sip of water. But what happens about the 10% that are slower than that? So it turns out that sometimes you will stand up a Lambda worker and tell it, go read this collection of S3 files. And the Lambda worker will go ahead and talk to S3 and say, please give me these files so I can run this compute on them. And S3 will say, OK, I got your request. And then it'll never get back to you. But the answer there is we have this idea of impatience, right? So when 99% of the requests have finished, we'll just automatically choose to retry the slowest 1% of requests. Because our experience with cloud-based block storage or object storage is that a request that failed the first time is not necessarily guaranteed to fail a second time. More often than not, the problem is with whichever server is handling the read, rather than the object itself on the back end being inaccessible. The other little caveat here is, again, this is cloud provider dependent, but we have been really, really frustrated with the fact that Amazon has designed AWS Lambda to work with API gateway, to work with web requests, to work with HTTP request response. So every request has to, in their view, serialize to either an HTTP request or serialize to JSON. But it turns out in our case, what we have is a bunch of protobufs that say, here's the encapsulation of the query specification, here's the encapsulation of the list of files. Why am I spending all this effort writing it into JSON and then reading it out of JSON to serialize it back into protobuf, right? Like, JSON is not a great high bandwidth, high throughput transport mechanism. So in some cases, we wind up sending the data by literally using S3 as a wire protocol. So we'll write the request payload into an S3 file and send a link to that instead. But it's a little bit frustrating and janky. Similarly, the return value. Let's suppose someone asks a really complex query that returns, 1,000 different groups and, has 100 or 200 or 500 different time granularity buckets. Well, great. Now that is more than 6 megabytes, and Lambda will truncate that response. So again, we have to use S3 as a message passing interface. And finally, I think there's this kind of question of cost. So yes, per millisecond of compute and per CPU millisecond of compute, Lambda is about 3 to 4 times as expensive as EC2. And this may seem like it's a horrible deal, right? Like, why would you ever voluntarily pay 3 to 4 times as much? Except for, if you remember that slide that I was showing you back here, right, of our utilization? Our average utilization is less than 5%, right? So effectively, AWS is only charging us for the seconds that we're running. So they're kind of effectively giving us a 20x discount on this compute. So the fact that they're charging us 4 times as much per second that we're actually running is vastly outweighed by the fact that they don't charge us when things are not running. But it is still something that we keep an eye on, because how many of you have ever accidentally set off a Lambda that set off another Lambda that then called the first Lambda, right? Like, how many of you have ever kind of created a Lambda loop? Yeah, those are no fun, right? So we don't have Lambda loops because our Lambdas are not capable of invoking other Lambdas, but we do have the phenomenon of someone, I don't know, something might go wrong and someone might run a query and they'll be like, oh, that's taking a while. I'm going to press run query again, and I'm going to press run query again. And suddenly that starts really, really adding up. So we've had to set alerts that are based off of the Lambda cost, and it turns out computing the Lambda cost is pretty straightforward because you multiply the duration of the invoke by the price per millisecond of the invoke, and it's glorious. The other interesting thing, I was actually talking with the lovely folks at the Seek booth yesterday about this, is even if we shrunk our Lambda bill by 50% or 90%, that still does not get rid of the kind of fixed costs regardless of the amount of time that your Lambda runs for, right? If you're sending a body that says, here are the files to read and here's the payload to execute, if that payload is too large or you have really, really, really tiny files and you have very many of them, suddenly the cost of telling Lambda that I want to invoke this payload, if your Lambda payload is, becomes a megabyte or 2 megabytes, they're going to charge you for that. They're going to charge you for the network cost to actually send them that request. And that winds up being not insubstantial. So that's the green cost here. And then there's the S3 request cost. So if your S3 files are not large enough, then you're going to have a situation where you're paying more to access the files for the privilege of executing a GET request against that file in S3 than you are for the actual computation involved. However, it's easy, of course, to go the other way, right? And if you create files that are a gigabyte in size and you only need 50 megabytes of that file, congratulations, now you're burning a bunch of CPU to decompress the file to pick out only the parts that you need, right? So there's this kind of interesting balancing act. And I don't necessarily see people talk about this a lot because people talk about the idea of, I'm going to use a Lambda power tuner, right? Like I'm going to optimize the size of my Lambdas to right-size the amount of CPU and memory according to the workload, which is well and good, but there's another dimension that you have to think about when you are doing big data analytics workloads, which is if you are using a scalable data storage solution like S3, the cost of that S3 also matters, so you kind of have to manage that trade-off of size of each object versus the cost to process each object. But one dimension that we do have control over is the kind of compute that we use. So again, this is kind of a little bit of a violation of the serverless abstraction barrier, right? Like theoretically, if I had a Python program, I could just stick the Python program up on AWS and tell them, hey, you make this Python program run. I don't care where, I don't care how, I don't care what architecture it uses. But in reality, it turns out that even Python programs, you might have native C bindings for those Python programs, right? Like you actually need to tell AWS, no, my Python program that I'm expecting you to run on AWS Lambda only runs on x86, or this Python has been built only for ARM. So there is kind of this control knob of what hardware do you use that your cloud provider may expose to you in the course of running your serverless functions. And some of those knobs for which hardware you want to use might offer better price performance. But the devil's always in the details of testing to your specific workload, right? Like there's this glorious marketing release from AWS that's on September 29th, 2021 that says you can get up to 34% better price performance. So we decided we were going to give it a go, especially because we'd previously found that when we were migrating some of our EC2 workload to run on ARM64 processors, that it was about 30% more cost efficient. So we were like, yeah, okay, that smells about right, up to 34% better price performance. So we tried it. And again, we were able to try this because, if you're using a language like C#, .NET, Go, right, like there's the ability to specify just with an environment variable or with like a compile time command that just says, what target architecture do you want to target? If you are using a language that doesn't have that, or where you're kind of using native dependencies that may or may not be compiled for the architecture, well, you might be a little bit more out of luck. But in our case, we were able to tweak an environment variable, produce artifacts for both architectures, and try it. But then you run into the problem of verifying, the cloud vendor can promise you the sun and the moon, but do they actually deliver for your specific workload? So we went ahead and we tried, we previously had success with some of our fixed workloads that were using EC2 instances or EKS, but we wanted to try this with Lambda. So we uploaded a zip file with our code that was compiled for ARM64, so we could run an A/B test of ARM versus x86. And it turns out that the cloud provider can say, we're going to discount the price of this by 20%, and they can say, in theory, your stuff should finish running 10% faster because the processor is 10% faster, so there's where they get that 34% performance number. Our experience was not nearly as rosy, at least and optimized for this workload. So we uploaded the 2 zip files, compiled with different options, and it turns out that the ARM64 option took literally twice as long to execute the same data analytics workload as the x86 version. So that was a little bit of a head scratcher for us. We were like, why did we see such good results with one workload and see such bad results on Lambda, right? Like, surely they're using the same processors, right? Like, it's all this new Graviton chip that they put out. So the first thing to do, obviously, is you don't just sit there with degraded customer experience while you're trying to figure it out, right? Like, you have feature flags. You have control knobs to say, I'm going to limit the blast radius of this feature, because otherwise, you're going to set users up for having a really bad experience. So I tweaked the control knob and immediately was shut it off, and our customers were back to seeing good results. So now kind of came the performance engineering exercise of, why was this so slow? So it turns out that, again, like, serverless functions, believe it or not, they run on real physical servers. So AWS had launched this in September of 2021, but they hadn't necessarily built out all that capacity to the same levels as they built out x86 Lambda, because x86 Lambda has existed forever and a day, right? It was one of the earliest products that Amazon put out. But this kind of pool of resources available to execute ARM requests meant that we were a large enough, when we just naively flipped that feature flag to 50%, suddenly we became the single largest customer of that new product that they'd put out. So that meant we were contending with ourselves every time we would say, I would like to run 1 million Lambda invokes right now, please. We would contend ourselves, and that would slow it down. The other factors were that we were using an earlier version of the Go runtime that did not have as optimized of a support for ARM64. In particular, this is kind of a little bit of compiler inside baseball, but like, it's a lot faster to pass arguments between your function calls in the registers rather than expecting to pop them to the stack and to push them back out, right? Like, it just makes a lot better sense to store the data in the registers, and Go hadn't implemented that optimization yet for ARM. And another thing that we found was that some of the libraries that we're using, because we have this trade-off of, again, going to the cost of the compute and the cost of the storage, we had decided, we wanted to compress our data before writing it to S3. But the problem with compressing your data before writing it to S3 is now you need to pay the tax of decompressing the data every time you want to read it. And if you happen to be using a library that does not have a native implementation and you are just running naive compiled code, it's not necessarily going to be super performant and fast. So we were able to schedule doing, turning on and off our feature flags and kind of profiling things as we went in order to determine when it was safe for us to proceed. And eventually, we were able to hit 99% of our Lambda executions running against the new processor architecture. And more importantly, right, like, we were able to actually save that money, that 20 to 30%. And interestingly, the way that we chose to optimize that, given the constraints of, it takes a certain amount of time to read a file off of S3. Each Lambda has a specific amount of network bandwidth available to it. The way that we achieved that savings was not by trying to shave down the amount of time that each Lambda took to run on ARM, but instead we said we're going to make our ARM Lambdas and our x86 Lambdas take about the same amount of time to execute any given request, but we'll shave off the amount of CPU and memory allocated to each Lambda worker because they charge you by the virtual CPU second. So that's how we broke what was otherwise shaping up to be a really, really bad cost curve, right? Like, we are on track to spend so much money on Lambda if we'd continued on our trajectory through 2022. But instead, we're actually just now in 2024 starting to see the levels of expenditure on Lambda that we were seeing in 2022. Now, would it have been cheaper to run all of this, to have our product be slower and just run all of this sequentially on raw VMs? Sure. But developer experience and flow are worth spending money on, right? So anytime someone asks me a question like, hey, is it worth it spending money on BuildKite or CircleCI? Right? Like my answer is yes, right? Like there is a huge difference between your build time taking 15 minutes and your build time taking 2 hours, right? That spending that, right, like throwing money at making your tests run faster is very much worth it so that you don't have to worry about, oh, I'm going to turn off these tests, or oh, like, I can't afford to pay for good observability, so I'm just going to go and use the shitty thing that sits there and spins for 3 minutes, right? Your developer time and your flow is so much more valuable than any amount of money, really, like almost any amount of money that you could spend on AWS Lambda like this. And the same thing goes for your data analysts. The same thing goes for your data scientists, right? Like this is not just an observability thing. This is any time that you have the ability to throw compute at a problem to make a engineer or developer or analyst happier, you should do that. So here are some charts and graphs illustrating that phenomenon of, sure, the ARM processors, right, when we starved them of CPU to the bare minimum, they might run slightly slower than the x86 workers with the way that we tuned it. But we are using less compute per worker to achieve that result. And also, each CPU millisecond was costing about 20% less. So this was a good outcome for us and a good outcome for our users because it meant that we have not needed to say, hey, by the way, you're querying too much, knock that off, right? But it's also, for us, it's not just about the money. Because it turns out, I'm really gutted that I missed the talk about sustainability in the previous block. It turns out that when you have information computing and technology, when you have data centers that are emitting as much CO2 as every single plane in the world, right? Like that is a lot of carbon emission. That is a lot of energy that is being spent potentially inefficiently, and we're making that problem worse with AI, where we're just throwing GPUs at it. But this is kind of one of our little ways of saying, these ARM processors, right, running this serverless workload against ARM, it isn't just cheaper for us. It also means that the data centers are consuming less power, and it means that the carbon emission associated with clicking that run query button is a lot lower. So my message to you, if you are thinking about applying these lessons at home, is yes, do this if it is appropriate to your workload. So most bulk workloads where someone is waiting for the response to come back will benefit from doing this. First thing that you have to do is you have to move that state from local machines onto object storage, right? If the data that you're trying to analyze is stuck on an EC2 instance or an Azure VM somewhere, right, no amount of parallelizing is going to help because it's going to be blocked on the network trying to talk to that individual machine to suck the data off of it. So we have to first make sure that we are tiering that data onto object storage so that any worker running anywhere in your cloud provider service environment can pull that data. Secondly, again, do not run one invoke per file, right? You have to think about, okay, what are my work units? What's the size per batch that kind of optimizes the startup cost associated with an invoke call versus the cost of potentially, you're running 10, you're querying 10 things in serial, 20 things in serial, right? What happens if one of them gets slow and it blocks returning the entire batch? Thirdly, you need to make sure that every object processed is independent of all the others, right? You need to make sure that you have a clean separation of kind of the mapping and reducing processes. Because if you do not have a clean separation of mapping and reducing, right, if your workload is highly interdependent upon previous results, you're not going to get good results because the whole theory behind massively fanning out and using serverless workers as your executors is that they shouldn't have to cross-talk with each other. They should only need to talk to object storage, and they should only have to report their results. And finally, you do need some sort of efficiency in your reducer function, right? If you are calling out 1 million invoke requests, you'd better have an efficient way of getting 1 million responses back and aggregating them together. So here are the dragons. Do not apply this if you have workloads that are latency insensitive, right? If you have a bulk analytics report of, here's the past quarter's financial results, maybe don't run that against Lambda, right? User expectation is that might take a few hours to run. That's okay. That is a cost issue. Again, if you were, right, if I were to change this time range to, right? So if I were to change this time range to 10 minutes, right, this 10-minute query should not wind up executing against Lambda, because that would be a waste to query 0 or maybe 1 or 2 files off of S3, but not like a whole bunch of them, right? That's better just computed locally. Third, because this is a workload that kind of blends serverless and serverful computing, it's important to coordinate with your cloud provider because they may have capacity planning considerations around if you expect to suddenly burst to a concurrency of 10,000 or 20,000 or 30,000. And then fourth and finally, whether you be adopting something like ARM64 or whether you be migrating your workload to serverless for the first time, you really need to do profiling of your workload, where you really have a situation where time is money, where every millisecond of execution results in you being sent the bill for that millisecond. It's important to understand, are you making the most of every single scrap of CPU time that you're getting, especially given, this is actually a really interesting thing that we found. One thing that we've found is that Amazon actually will give you at least on x86, they'll give you the worst CPUs they have in their entire fleet, right? They are selling you their spare capacity. So you will find literally 2.5 gigahertz Xeons from 10 years ago that are running Lambda executions. It's truly strange. Let me show you what I mean. Source name is Lambda, and I'm going to group it by CPU info. Let's see, CPU info, CPU megahertz. Let's do that. So, yeah, literally, right? I can see, okay, roughly rounded, right? A majority of these executions. Oh my God, that's wild. A third of these executions are happening on 2.2 gigahertz machines, right? Literally 10-year-old hardware. So the behavior that you are seeing running your data processing workload on the latest and greatest instances may not be the performance that you actually see running in parallel on Lambda. So tune everything properly, right? Tune the items per invoke, tune your CPU RAM ratios, tune your batch sizes of the amount of data per file stored in S3. Make sure that you're doing optimization, make sure you're profiling, make sure that you are looking for opportunities to save on waste. Make sure that you're measuring everything as you go, right? You have to make sure, especially if you're paying for it, that you are getting the results that you expect, and that if there is something that is causing you more cold starts, you want to know about it. If your cold starts are taking longer, if there's some kind of regression, you want to be able to find out about it. And that's where, again, having that metric of, hey, by the way, did you know you just spent $10,000 in one day, right? Having an alert go off is really helpful to kind of provide that break against something getting out of control. And if you do wind up choosing to adopt ARM64, you can save a lot of money and make the planet a better place, but it does require a little bit of elbow grease, right? You have to make sure that your build pipeline is producing artifacts for the right architecture, that your clusters or that your Lambda functions are configured to be able to run either architecture's configuration, and that you have the control knobs to flip back and forth between them, to A/B test, to kind of measure and tune it in before you roll out to 100% of everything. So at the end of the day, nothing matters unless developers are happy, and also that your CFO is not mad at you because of the cloud bill. So that's what I have to share with you today. If you're interested in more details about kind of this, about the system that we built, that was a little bit of a predecessor / developed in parallel with ClickHouse, you can check out the O'Reilly book that I and my co-authors wrote. And here's a final picture of Flurry, who is an adorable golden retriever and that I love very much, and that I want to be happy as well. Thank you so much.